Hello, teacher and everyone. My name is Karan Gupta, and today I would like to give you a quick uh, introduction, not only introduction, but today we are going to solve a beam problem. Particularly, this part is more related to the civil structural analysis in journal and how we deal with it. And Today, this is the second series of example, and today we will see more in detail about a problem statement, how to solve that problem statement in journal, particularly into a software called I mean this Abaqus CAE software, and try to check it out how we can accomplish the task. So we can see quickly this is the problem statement that we have right now. So we have to use any of the finite element program. So we have to model a cantilever beam. We have to use a four-node plane stress quadrilateral fully integrated elements with a thickness of 1 unit. That's what we will check it right now during the uh, solution, and we have to use a Poisson's ratio of 0 0.3. So in our case we will use 0.3, so particularly you guys can practice with 0. We have to solve two things. So we have to check it out the deflection at point A, which can be seen here, and also we have to check it out the stress components at point B, where the fixed boundary conditions will be there. uh, Also we have to check it out, and just we can do all other things as per our accountability to understand this particular problem. So this beam is particularly 5 units of length and 1 unit of length in the vertical direction. So it's a 2D case in general, and we have a Young's modulus value of 10,000 units. It's You can assume any of the unit for your use case, and Poisson's ratio of 0 and 0.3. So let's try to first of all do it in particular Abaqus. As we have already seen in our first example that how this interface how we have to quickly interact with this interface. So make sure whenever we do anything, we have to do step-by-step process, like first initiate with the part, property, assembly, step interaction, so on and on. As the examples goes on and on in this series, we will see how we can use all other modules that we haven't selected so far. But as initially we say like we have to start with the part. So we double click here. We can just model today. We are just modeling the beam internal, and it is a 2D deformable. And as we know, like base feature is not today is not wire is mostly for the one dimensional stuffs, and for shell it is like 2D. So that's what we are doing. Approximate size we all know. So since we have to check the length of it, so we can see it is 5 unit in x direction and 1 unit in y direction. So that's what we have to do it. Select the rectangle, just give the initial coordinate 0 comma 0, and then now it is free to move, and then we have to give 5 comma 1. So that's how like we just create a beam, and just say click done. So this is what our cat file is already generated with us. Now we have to assign the property. To assign the property, we have to give a particular name to it. So let's say today again we are giving it steel, and now we can define the density, mechanical properties, thermal properties. That's what we will see later. Today we are only seeing elasticity. So to the elastic again, like if you go more deeper into the theory part, then we have to understand even in elastic we have different material models, like an isotropic, orthotropic, isotropic. So the simplest one is the isotropic. That's what we selected today. Young's modulus. So if we see the problem here, it's given 10,000 of any unit. So we give the same. It's 10,000. Now the Poisson's ratio given is like 0.3. That's what we have given here. Nothing more than that we have to define here. That's it. It's done. Now we have to define the section. So for defining section, let's say it's a beam part that we are going to deal. So either you can define with the help of this beam, the same beam element, but today like the type of the element that we are going to define is the solid part, solid and homogeneous part for this particular case study. So we selected, okay, so we have already defined the material. Again, the plane stress and strain thickness is something like probably we have seen. It is the given is like only 1 unit of thickness into the page, but let's say if it's 2 and something more like that, we have to activate this and have to give a particular like 2 or 3 as per our requirement. But if we say it is 1, so let's make it by default. We don't have to change it. Okay, now we have to assign the section. So select the regions to be assigned. So we select this particular region to be assigned. We say done. Okay, then beam we only have only one type of section, so by default everything is all okay. If there are some other also, then you have to select what exactly you want it, what type of section you want to define. Say okay, and once the color gets changed, everything is all fine, which means we have correctly defined it. Now another part is to do assembly. Again, we have only one element. If we have more number of elements, let's say nuts, bolts, and other type, then this element we have to select each and every one here. For that, we have to go to the instance. We can also go here, for example, in assembly. Just put the plus button where you can just have all the drop down stuff. I mean all the drop down text. So we have to click on instances. So we can click on, we have only one. So beam is only one that we have selected. So we say okay. So we got it. Let's say if we have another part of it, so we can just quickly go again. Then we can just put it back here in this particular, but we don't have it, so we just remove it. That's it. So the point is, like, in this only phase we start doing analysis. Before that, whatever was the CAD only. So we have defined the assembly. Now it's the step. So now we have to understand what exactly we have to define. We have to define, one of them is a boundary condition here, and one is a load condition. So we go to the step here again on the left side panel. So initial, the first step is already defined, which only tell us the initial boundary conditions. So here we cannot define the load. So to define the load, we have to create another one. Let's say apply load. Make sure, like, whenever we have to create a load, or we have to create a new step, make sure to give a proper name to it. It's an apply load, and make sure it is static journal for this case. Soon after some time we will see some other analysis also. Now again, this part is really important for us for today's analysis. We are not going to go so much in detail, but what exactly is happening, whatsoever the load we apply, it used to be regulated by the CAE software from this particular I can say the incrementation size. So let's say increment, if I try to change the initial or maximum size and the number of increments, it directly applies to the load. Because what happened, like in Abaqus CA softwares, everything happens respect to the numerical methods or incrementations. So that's what, like, we will see how exactly solver is to solve it. So if I say, let's say make it 0.1, then it is a 10 percentage of my current load has been applied as the first step. So this is how, like, in journal it happens, but this is as of now automatic, basic, and this is NLGOM, means nonlinear geometry. So for example, for whenever there is a highly nonlinear analysis, then we have to make it on. But it's a good way if you always make it on. Doesn't make any good, and I mean, not a big issue to you. Also, we have a time period. So it's a pseudo time period for let's say static analysis. It gets changed when we try to understand the dynamic analysis. So let it be by default. That's it. We are all done with this step. And then we have to define the load condition. As we define, like, we have to first make the, let's say, the boundary condition, the initial boundary condition. So let's say that was the boundary condition fixed boundary condition. Make sure we have to apply it to the initial part, to the initial step, and then we have to give the displacement rotation. We continue, and then we select the edge where we have to define the, because if you can see the example, this is where we have to define it, and we just click on OK. So again, U1 and U2. So make sure, like, UR3 is not activated because the type of beam that we have taken is a solid beam. If we have taken the type as beam that is defined earlier, then there we have to define the rotational degree of freedom also. For all the solid bar and truss elements, we don't have a rotational degree of freedom. For buckling analysis, it's going to be a totally different case, but here we are not going to deal with it. So define U1 and U2 as 0. It will fix that particular boundary, and that's it. Now we have to apply a load. So we say apply load, and again we can see it's not going to apply at the initial, but we will apply to the apply load still. We just give a concentrated force. We have to give to this particular edge, and then we will check it out how much we have to give. It's 1 unit of force. So we go to the done. Then we have CF1 is the axial axis and CF2 is the vertical axis. So we have to apply not to the axial, we will just give 0, and we have to give for a vertical 1. Then we'll check how it is. So it is applied at the top side, but if we see it should be applied to the downside. So we have to go to the load here on the left side, double click here and change the direction. Just keep -1 and it will just change the direction. That's it. So yeah, everything is all fine. Now we have to define the mesh. So for defining a mesh, we can either define it with the seed edges or with the whole seed part. I mean the whole part. If we define it like that, for sure, first we have to define the part. Then we have to define it like it's a global size. So 0.5 will be applied to this whole part. Like each quad elements will be of 0.5 only. So let's check it out. It's going to be like that. Okay, then we have to mesh the part. Say yes. This is how it is generated, but I don't want it. I just want with the help of seed only. So I have to select a particular edge for the seeds. Let's select this. I said done. Then we can select it by the size or by the number. Again, we selected by the number. I want 4 on this particular edge. And it asks like, do you want to delete the mesh that you have generated before? You said yes. So we will delete it and we will apply it. And we said okay. Then we will see again, mesh it. So we can see here like 4 nodes were generated in journal. So again, this is all okay. You can play with this mesh and you can make a really good mesh, or it really depends on your accuracy type. So I just want at the top edge to be even much more. Let's say 15 is good for me. I said okay, delete the previous mesh and apply it here. Okay, so now the important part here is I also have to define the element type. So let's say to define the element type, it's really important that we have to choose the correct family. So make sure like this is a plane stress problem. So we have to select the plane stress problem, and then we have to use the geometric order. It's linear or quadratic. Again, everything is defined in the sorry what exactly linear and quadratic means. So linear elements and quadratic elements, how the nodes are defined. For linear, it is only 4 nodes, but if it is written like 8, then we have to select it like if it is written here as 8 node, then we have to select like the quadratic geometric order. Again, this reduced integration is by default selected, but make sure here they have asked for a full integration. So again, we have to really go through to the theory part because that's where like the all the information is defined. So we have to remove this so as to get a full integration, and that's it. We have to click OK, and we have to mesh the part. So yeah, this is how the geometry is defined. Now nothing else, just go to the job and try to submit it, and make sure always try to save it in a particular directory. So if you don't save it, it will directly go to the temporary file. So defining a directory is really important, because if I don't do it right now, will try to save it in the temporary file. So I just want it in temporary, it's all okay. And if you want, you can just put up into a particular file so that you should always know where exactly the files are going. So we create it and we say this as a beam analysis, and we say continue, and this is by default, it's all okay. Then we have to submit, and after submitting, we can also try to monitor it. And actually, the point is we also have to understand how exactly this analysis happens. These particular, when you submit it, it tries to create an input file .inp. That's what you have done so far, like all the boundary condition, whatever you have put right now here. And then later on, what happened is like a solver, Abaqus solver, try to read that input file, try to solve it, and then you get the analysis. So this is how it happens. So we go to the monitor. We can see, okay, in a single iteration, we will see it later. In a single iteration, it completed. And then we go to the result part, result analysis, and go to the undeformed plus deformed part is this one. So here we can see the one minus stress, and also we can check it out the deflection or the displacement. So as we can see, what exactly the question asked was like try to determine the deflection at point A, which means the magnitude. We have to check it out. We can select here rather than magnitude. We can select in vertical direction is U2. Let's select U2 only, and so deflection at point A. So which means we have to select it here. So we have a option called a probe. So we can just, with the help of probe, we can try to figure it out what exactly is the deflection. So it's probably downside. I cannot see it, but that's how like we just understand. Then we also have the one minus stress. Let me see where this problem is there. So if I try to, okay, so if I go to toolbar and let's say I don't want use, I don't know. Yeah. So the point is that prop values you can just find it out from downside, and with that particular thing, yeah, here it is. So we can just check it out with the prop. The one minus stress is selected as a default. So what we have to do, we have to check it out the stress component at point P. So here we have to check it out the stress component. We simply go here and just put it here. So it is 28.851 any particular unit. And now what I have to do, I have to now we have to select the deflection at point V here. Again, I have to go to the prop and its nodes. We have to select node. Its U magnitude is all fine. And then you have to select it here. So it is like 0.049 of deflection downwards. So you can even select it here like U2, or to be more precise. Then again, you go to the prop, then select it, the U and U2, just select here. This is in the negative direction, so that's why it is minus 0.4. So yeah, that's how like we deal with this particular problem. I hope like you guys understand each and everything, and soon after later we will also do some more other type of problems that deals with the buckling analysis, for example, other part of it, and dynamic analysis also. Yeah, thank you very much.